OK, so in this talk, I'm focusing on electronic commerce for cloud computing. And in particular, I'm looking at the question of designing online scheduling mechanisms, which is basically assigning selfish jobs to server times and charging the jobs with appropriate payments. Let me jump directly to the setting of online scheduling. We have online selfish jobs that arrive from time t equal to 1 to capital T. And then we have a cloud service that has M servers. And the objective is to design an online scheduling mechanism. If you focus on one selfish job, the job has 4 parameters in this setting. Its arrival time, its deadline, which is the latest time that the job needs to be finished, its length, which is the number of time units that the job requires, and its value per length, which is the value that will be generated by finishing 1 unit of this job. We are interested in a regime that these parameters are upper bounded by constants, and t, the time horizon, goes to infinity. Now, what is an online scheduling mechanism? It has 2 steps, an admission control and a scheduling step. A job reports its parameter to the mechanism, whether it gets rejected by the admission control or gets admitted. And once gets admitted, the scheduling step assigns the jobs to a subset of time units called allocation or tau j, and charges the job with some non-negative payment pj. OK, so let me go through some definitions. We are interested in quasi-linear selfish jobs, which are the jobs that the utility they get from allocation is going to be value minus payment times the length of the job. These are per length. We are interested in truthful scheduling, which are the type of mechanisms in which no user is bettering off by misreporting any of the parameters. And we make this assumption that no job is allowed to report an earlier arrival time. We look at prompt scheduling, which is the case that the allocation and payments for a selfish job will be determined at the time of its arrival. And we consider 2 settings for scheduling: the clairvoyant scheduling, in which the jobs report their length once they arrive, and non-clairvoyant scheduling, in which the job doesn't report its length, and the platform only realizes the length once finishes the job. We are looking at social welfare maximization for online scheduling mechanisms that we are looking at. And we define the social welfare of some mechanism M up to time t to be the total value generated due to scheduling jobs from time 0 to t. OK, so what do we know about mechanism design in this setting for social welfare maximization? Actually, the worst case mechanism design is pretty hopeless. In fact, we know even for tight unit jobs, there exists no deterministic truthful mechanism that can achieve a sublinear competitive ratio. And even if you throw away the incentive constraints and look at the online optimization problem, it is again hopeless. And there exists no sub-polylogarithmic competitive algorithm for this setting. Despite these negative results, we have a remedy, which is the following. Suppose you give me a family of online scheduling mechanisms that are truthful. OK? So these mechanisms might be some parameterized heuristics that work well in practice, or they might be some natural mechanisms that people use in practice, or there might be, let's say, a family of mechanisms that, for example, we know they work well under a stochastic setting of jobs. Now, here is my goal. I try to design another truthful online scheduling mechanism that can compete with the best of these family members. Or in fact, I try to basically learn the best members in this family. And now I'm looking at actually the worst case or adversarial jobs. Besides being interesting by itself, there is a nice implication of such a design. In fact, if you look at the Bayesian setting for online scheduling mechanism design, then which is a setting that the jobs are drawn randomly from some prior distributions, we know, due to a recent result by Chawla et al. In 2017, that actually a simple family of online scheduling mechanisms are near optimal in terms of social welfare. So what are these mechanisms? They are basically FIFO scheduling combined with pricing as an admission control, which is the case that you post a price, a job arrives, you admit the price if the value is greater, admit the job if the value is greater than the price, and then the job goes to a FIFO queue to be scheduled. So far, so good. But there is a caveat here, which is finding the optimal price. And in fact, finding the optimal price to offer in your mechanism requires exact knowledge of the underlying jobs distribution. And even if you know the distribution, it has been shown that the problem of finding the optimal price will be boiled down to solving a large linear program, which is computationally challenging. Now here is what we get. In fact, if you can learn the optimal in hindsight in a family, let's say this family, then basically you can learn the optimal Bayesian benchmark by multiple interactions with the jobs in an online fashion. OK, let me formalize this question in the following way. Suppose we have n truthful online scheduling mechanisms, OSM1 to n. And I define my benchmark to be the best of these mechanisms in hindsight in terms of social welfare, denoted by opt. And then for a particular mechanism M, I define regret to be basically opt minus the welfare that this mechanism gets up to time t. Now, here is the research question we are addressing formally. Given access to these n truthful online scheduling mechanisms, can I make another online scheduling mechanism that guarantees the following two? First, my mechanism be truthful. And second, the average regret that I get converges to 0 as t goes to infinity, which is known as vanishing regret. And here is our result for the clairvoyant scheduling. We actually show there exists a truthful online scheduling mechanism that admits a regret of upper bounding by order square root t. And this is indeed tight, meaning that there exists an instance of jobs with FIFO pricings that admits the regret at least big omega square root t. In the remaining of this talk, I am trying to show you how the upper bound works. And hopefully, I can explain what does happen in the non-clairvoyant scheduling and what is the technical challenge that we have and how do we address that technical challenge to get similar results for non-clairvoyant setting. OK, so the main idea to get upper bound is using learning. And in the clairvoyant scheduling setting, we actually use learning from expert advices, also known as full information online learning. It is not that hard to see that in order to apply online learning, all you need to do is to associate one expert or arm for each online scheduling mechanism, and then define the reward of arm I at time t to be the value that will be generated by running this mechanism at time t. And now, having these reward functions, we can just send a query to some expert algorithm or an algorithm for the online learning with full information. OK, so far so good, but here is a challenge. Suppose the algorithm that you are following tells you to switch from some online scheduling mechanism A to another online scheduling mechanism B. In a magical world that we can swap the state of the scheduling, which is the current schedule that the machine is running, then you won't violate truthfulness of the mechanisms, and there will be no social welfare loss. So it will be really great, and you get exactly the same regret guarantee of this expert algorithm. However, this is not the reality. And in fact, we need to do some sort of a smart switching from A to B, which is a switching mechanism that satisfies the following two. We need a switching mechanism that the social welfare loss due to switching will be upper bounded by some constant c. And also, if both of the mechanisms are truthful, due to switching, we won't lose truthfulness, and the final mechanism remains truthful. Now, if you have such a mechanism, it's not that hard to see that actually the problem will be reduced to a learning problem, which I call it expert with switching cost, C. And this is indeed a well-studied problem in the literature. So what is this problem? This is the following problem. It's like learning from expert advices. But once you switch from one expert to another, you incur an extra cost C as the algorithm. We know that, for example, due to the work of Chawla and Van Pal in 2005, follow the perturb leader gets the order square root t algorithm for this problem. And therefore, if you use any algorithm with such a guarantee from this problem and do this reduction, you can get exactly the same regret bound for our problem as well. Now, all I need to show is how to design such a switching mechanism. And this is the aim of the next couple of slides. So let's try some natural things. So suppose I want to do switching at time t equal to 0. There is also another relevant time, t equal to d max, which is the time by which all the jobs that have arrived before 0 are going to expire. Suppose this is the schedule of A, and this is the schedule of B, and these downward arrows are indicating deadlines. Now, the first thing I try to do is the following. So I stop the schedule of A, because the switching happened exactly in the middle of doing this job. So 1 will be rejected. And then I try to do exactly the schedule of B. So 2 will be scheduled, and then 3, and then 4, 5, 6, 7. So the social welfare loss is going to be upper bounded by whatever you lose between this interval, which is OK, it's affordable. But the problem is with truthfulness. In fact, if you think about this job, then it has an incentive to report a later arrival time. And this is not going to be incentive compatible. So let's try another thing. So I do or finish whatever schedule A was doing. So I finish 1. And then I basically reject all the jobs that have arrived in the interval 0 to D max in the schedule B. So 2, 3, and 4 will be rejected. And I catch up with the rest of the schedule of B. And with the schedule 5, 6, and 7 in this order. This is, again, has bounded welfare loss. But again, the problem is if you look at job 4, then it has an incentive to report a later arrival time, let's say D max, and it still gets scheduled in the final mechanism. So this is not going to be truthful. So as you will see, we actually need to stitch the two scheduling mechanisms in a smart way to preserve truthfulness. And this is the right way of doing it. So I continue whatever A was doing. So I hold to all promises that the schedule A had. And then I block all the times from 0 to D max. Therefore, if there is a job whose deadline is before D max, it's going to be automatically rejected, like job 2. And then I try to push all of these jobs whose deadline is after D max to be started at D max. And I schedule them in an order respective manner based on their arrival order. So what happens is, for example, 3 gets rejected because there will be no time for doing 3 if you want to start it at D max. The deadline is here. But you can do 4, 5 unfortunately will get rejected, and 6 and 7 will be scheduled. Now here are my claims. This is going to remain truthful. I'm not going to show you the detail of the proof, but the key property that the previous construction satisfied was the fact that none of the jobs was finished at an earlier time than their finishing time in the schedule of P. But let me show you why the welfare loss is bounded. In fact, if you think about the previous construction, then the welfare loss is basically due to the jobs of B that you drop. You hold to all the promises of A. But then you block all the times between 0 and D max. And the welfare loss in this interval is going to be upper bounded by M, V max, D max. Let me remind you what are these variables. M is the total number of servers. V max is the maximum value. And D max is the length of the interval. But that's not the only source of the loss. In fact, you drop some of the jobs in the schedule of P after D max. And the jobs that you schedule are only a subset of the schedule B. But it is only enough to count the number of times that B scheduled something, but the final switching mechanism didn't, which we call them free slots. And then there is this nice observation. If there is a free slot at time t, then that means the final switching mechanism never replaced a job after t. And therefore, if you want to count the number of free slots, you need to just look at the jobs before time t. But then all of these jobs are going to expire by the time t plus d max, which implies that all the free slots are in the interval t to t plus d max. And therefore, the total welfare loss due to those free slots is going to be again upper bounded by m v max d max. Putting these two together, you get the total switching loss, which is a constant. And then putting these two together with the reduction to expert bit switching costs, you get the regret bound that I showed you in a couple of previous slides. OK, so let me switch gears to non-clairvoyant scheduling and give you an intuition what's the technical challenge here. Let me remind you what is the non-clairvoyant. In the non-clairvoyant, you won't notice the length of a job until you finish doing the job. OK, now suppose there are the jobs, as in this slide. There are two special jobs, J1 and J2. Now suppose I have two online scheduling mechanisms. One of them starts the schedule with J1, the other one with J2. So if I start with J2, then red jobs are going to be scheduled. And if I start with J1, then the blue jobs are going to be scheduled. And obviously, the second mechanism is much better than the first one. But the problem is the following. So if you run any online scheduling mechanism, and it starts with J2, which is the wrong one, it will never, ever notice that J1 set of jobs were good at the first place. And that's because you won't see the length of these jobs because they won't be reported to the platform. Therefore, it seems it's kind of hopeless to fight against the unmodified benchmarks in the non-clairvoyant setting. And in fact, you can make it formal by showing that there exists an instance with FIFO pricing that admits a regret of at least big omega t or linear regret, which is bad news. But then there is a cute trick that can make this problem interesting again, which is restarting regularly at random at times so that you fight with the timing issue, which was the source of the problem here. And this is indeed what we do. So let me define you what is the meaning of truthful random restarting. You can think of the following operation. At each time t, I flip a coin. And if the coin flips heads, I do a truthful switching from the mechanism to itself. This is what I call random restart. The good news is, if you think about the stochastic jobs, then these random restarts are not going to harm you much. And in fact, in the stochastic setting, if the probability is set smartly, then this is not going to be a major source of welfare loss. And now there is a hope. So you might be able to compete with the best of these restarting online scheduling mechanisms or restarting benchmark, which is actually what we get in the bandit version. So I'm not going to explain the details, but the idea is your algorithm also randomly, regularly restart, and at each restart time, send the query to some multi-arm bandit algorithm, and update the reward of the scheduling mechanism that was playing since the last restart, use it as an unbiased estimator, and continues. So this is the result we get. We actually show that with respect to the restarting benchmarks, you get an order till t to the power 2/3 regret, and this is indeed tight. Let me summarize. I was looking at online scheduling mechanism design, and I showed how you can basically compete with the best of a set of given online scheduling mechanisms by aggregating truth and regret, by using tools such as truthful switching, truthful restarts, and reduction to expert with switching costs and multi-arm bandit, and why in the non-clairvoyant restarts are required, and our results can be generalized to the non-clairvoyant using this technical tool. There are some open problems. I think the interesting one is assuming that the server has multiple resources and there is a price for each resource, and now you're pricing those resources. But then the question is, can you do it efficiently? And there is this recent progress on Oracle efficient learning that might be a window of hope to attack this problem. Thanks for your attention.